in the model, there are many points of intervention where we could try to do a better job. For example, we could try to, here on the industry side, I'm trying to get a mouse here, so we could be more careful about our use of water, exercise stewardship over water. We could try to change the price structure so that people are more accountable for the use of water because of economic signals. We could do better with our agricultural practices. We could introduce green infrastructure in our cities to augment the gray infrastructure, which is so costly today. So I could go on, and I won't go through this whole diagram. But you can see that in this systems model, you can start to think about points of intervention, and you can think about the costs and the benefits of intervening in different ways. And I believe there is some portfolio of new technologies and new practices that we could adopt that will allow us to do a much better job on stewarding our water resources. Now with New England, we looked at a particular problem. And this problem exists throughout the country, but it's a particular concern in New England that we have an excess of nutrients flowing into the waterways, mainly nitrogen and phosphorus. And in New England, it's mainly nitrogen, actually. And most of the nitrogen comes from wastewater treatment plants, which have a lot of organics basically flowing through those plants. And there are a lot of nitrogen compounds that are emitted and are very difficult to treat. Now, what happens is, of course, these nutrients cause problems in the water. They provide nourishment for organisms such as algae, which end up starving the aquatic ecosystems, and we get what we call dead zones. The largest dead zone, of course, is in the Gulf of Mexico. But these problems exist throughout the country, and they're a particular concern in New England because New England is so dependent upon water for its major industries, including fishing, tourism, and recreation. And so they've been exploring different ways that they can deal with this nutrient problem. A lot of the nutrients come from non-point runoff, for example, from fertilizers or from deposition onto pavements, so you get stormwater runoff. And as you know, storms have been getting more violent lately, so these episodic events can be very damaging to ecosystems. So how do we address this problem? Well, we focused on a particular watershed. It's a Narragansett watershed. It occupies a part of Rhode Island and a couple of towns in Massachusetts. And this watershed, in case you haven't been there, it's a beautiful area. Newport, Rhode Island is located there, Providence, Rhode Island, many beautiful beaches and so forth. Tourism is a very important industry there. And so we were working with New England to come up with what we call integrated strategies for nutrient mitigation. In other words, let's not just try and treat the water and remove the nitrogen, because that's pretty expensive. It's also very energy intensive. So while we might remove some of the nitrogen, we end up generating more greenhouse gases. Not necessarily a good deal. And we also spend a lot of taxpayer money. So maybe there are other ways. Maybe we need to better understand both the causes and the impacts of nutrient pollution rather than just doing the traditional thing, which is go and treat the hell out of it. Okay, so now the nitrogen cycle is pretty complex. I'm not a real scientist, by the way. I'm a mathematician, so I don't understand most of these things. The microbiology, the atmospheric chemistry, the dynamics of how nitrogen flows through the environment and is transformed into different types of compounds and eventually ends up affecting organisms. So I depend on other scientists to help me understand these phenomena. What we're trying to do is to couple together the knowledge from these different fields so we can understand the root causes, the dynamics, the effects, and the possible interventions associated with nitrogen pollution. We've developed what we call a systems model, which is a fairly high-level model that enables us to understand these phenomena in an integrated fashion, but in a very approximate way. We don't try to model all these systems in exquisite detail, because that would be impossible. It would be a research project that could take 100 years. So we don't have the time to do that. What we try to do is to capture the important details at a high enough level so that policymakers can understand it, and so scientists can contribute knowledge to this sort of integrated understanding of nutrient pollution. There are many uncertainties. The science is not settled. In fact, our scientists, we have a lab right there in Narragansett, and our scientists there, they're among the top scientists in the world in this field, still have not been able to model the dynamics of the bay successfully because of the marine freshwater interactions, the stratification, and there's a lot of complexities in trying to predict the behavior of pollutants in that aquatic environment. But we can take what we do know, we can try to piece together the available knowledge, we can make some assumptions about what we don't know, and we can start to explore what are the policy options available for decision makers who need to take action today. They cannot wait 5 years or 10 years for our research programs to complete. Well, the first thing we did was to do a sort of a overall mass balance for the region. I call this the plumbing diagram for the Narragansett Bay. So it's a crude representation, but it's very helpful to understand where do the water flows come from, where does nitrogen enter the picture, and what are the different pathways that the water and the nitrogen can take. So this is purely a physical model, and that's a good first step. And then, of course, on top of that, we need to understand all these different systems that are interacting. So we've developed a model based on system dynamics. I'll tell you more about it in a couple of minutes, where we try to capture the important industries, the key stakeholder groups, and the different environmental compartments or media that are all interacting in this integrated system. So you can see some of the subsystems that we looked at there. Each of these subsystems is represented in the model very crudely by a set of differential equations, basically, but sufficiently so that we can start to understand the dynamics and the behavior over time. So we built what we call a triple value simulation. It's based on a package called T21. Has anyone here ever heard of T21 or the Millennium Institute? Can I see a show of hands? This is a small group, but they have had a tremendous impact on the modeling profession. In fact, UNEP, the United Nations Environmental Program, recently came out with a global model, what they call the green economy model, which utilized this T21 platform. And we've been using it here in the US for a variety of applications. It's a very powerful model. It's based on work that was done for years by the World Bank to look at investments in foreign countries. And they were using it to try to assure that, for example, when you build a plant, say in Mozambique or someplace, that you're not displacing traditional lifestyles and damaging the environment and so forth, and so that they want to be sure that the benefits outweigh any offsetting adverse effects. So these models have evolved over a period of several decades. How many of you have heard of system dynamics modeling? Show of hands, please. Okay. So you've probably seen system dynamics applied in more limited situations. This is one of the most complex and broad scope system dynamics models in existence. And we've been able to customize it to specific regions in the US. We started in Ohio. We have a model of the Ohio economy, which includes natural capital and social capital. And so this piece focuses on the Narragansett watershed. It's even more focused. And I do want to say, this is my standard disclaimer, all models are wrong, some models are useful. You've heard this before. It's very important to keep reminding people, we don't think we have all the answers. We know that our model is crude and approximate and probably wrong, but it is helpful. It helps us to explore the space of possible opportunities and the potential consequences of our actions. There are many other models that need to be used to support this systems level model. This model is used for policy making in a very broad sense, but it cannot be used to actually verify scientific predictions. We have to go to more detailed analytical models and environmental models. And in fact, if you want to make a decision about a particular water treatment plant, you need a very detailed place-based model that takes into account all the local factors, the geographic and environmental factors, and the population factors in that place. So we have no illusions about the accuracy of what we're doing. However, we do believe that this model serves a purpose, and we've we've engaged with stakeholders from the outset. Here are the, I'm going to go quickly because I'm running out of time here, I know, but these are some of the sub-watersheds that we looked at, and we modeled the nitrogen loadings. So you can see these are the current loadings in 2011. These are based on empirical data. And then we were able to forecast the loadings through 2030. You can see there's some growth. I'll go back and forth. So there's a little bit of growth. There's a change in the pattern. That gives us a starting point then for looking at the impacts on the watershed. We also looked at a variety of policy interventions. You can see some of the things I talked about before are being considered by either EPA or state or local policymakers. And there's been a lot of discussion. There have been studies and various commissions looking at these different options and trying to understand which is best. For example, a lot of people are interested in smart growth and what they call low impact development, because the population will grow there, but maybe it can grow in a way that has a gentler impact on the water resources. This is the only real technical slide I'm going to show you. It shows the causal structure of the model. And you can see there's a variety of feedback loops. So we start with the nitrogen loadings or nutrient loadings here in the middle, if you can see this. So there's the nutrient loadings, and then that causes algae blooms, which causes ecosystem impairment, which causes reduction in finfish and shellfish, which can hurt fishing and tourism, which lowers the gross domestic product for the watershed, which affects disposable income, which affects municipal tax revenue, et cetera. So there are all these feedback loops going on. And this is a very broad brush description. This doesn't show you all the details of the actual model. It's sort of a high-level summary picture. But we did successfully develop the model. We've shared it with stakeholders. This is a work in progress. Oh, by the way, here are the interventions, some of the points of intervention that are possible. We developed a graphical interface which allows us to share the results of the model with stakeholders that don't have a technical background. So it's sort of a dashboard approach where policymakers can try out different scenarios on the left-hand side. They can go over here and use some sliders and change some variables and see what the impact is on the model. And on the right-hand side, you have various indicators over time. And we can predict the behavior of these different indicators. I hesitate to use the word predict, but we can project at least the behavior in the future. We can do sensitivity and uncertainty analyses. So we can explore the effect of assumptions and uncertainties and understand, if you will, the envelope of possible futures that would result from different types of actions. So I'm very encouraged by this. We started this last May. We had a model developed by October, which we shared with stakeholders. We're now entering phase 2, where we're going to further develop the model. So I'll leave you with this thought. We've got to think differently. Sustainability is a huge challenge. What I've been trying to do is bring the best available tools, analytical tools, to bear on this enormous challenge. And we think we're making some headway. And I'm happy to say that EPA is actually an innovator in this space. And so hopefully more to come. And I hope I can share this with you in the future and talk about actual decisions that have been made as a result of the model. Thank you very much.
Is the Narragansett Bay project, is that available to look at now? Is that available to the public?
Yeah, we have a draft report. It has not been released yet. For EPA people, I can certainly share information. So if you contact me, I can share with you some of the early results.
Thank you, Joseph.
Sure.
Is there a lot of GIS information and land use in this model?
We did not try to develop a GIS type resolution of this model. Although there are GIS models that are being used in the region and are actually contributing inputs to the model, and certainly the results of the model